Ready? Last time I was talking about material selection, and the point she should have taken away that it's multifaceted. There's no one set of properties or whatever, and you can't solve all problems by choosing a better material. You got to use design as well. Structural materials usage is strongly influenced by cost. In this course, we're interested in fabrication of structural materials. I'm not talking about electronic materials, but structural materials are used in large volumes. You build big bridges, not small bridges. Okay, so a lot of material, buildings, bridges, cars, trains, and when you're using a lot of material, cost is one of the primary considerations. And because that's true, one structural material stands out above all others, and that's steel. Now, concrete is close to it, but the problem with concrete is that it doesn't have as good a fracture resistance. But steel has an unusually beneficial combination of cost, strength, toughness, fabricability, and a number of other things. And that's why we use it so much, and it'll be around forever. In spite of the fact that nobody's making any money in it, that doesn't mean that there's some investor can't come and buy the plant for a song, try to make some money out of it, and sell it to the next sucker. Okay? And that's what's happening in the industry right now. Now, so far as different types of materials, we talked about wood last time. And I wanted to, since this is a course for people interested in shipbuilding, if you're really interested, I have a tape, a 1-hour tape, which is one out of a series of 20 on a PBS special called Out of the Fiery Furnace. This is the history of metallurgy. Actually, history of materials to a certain extent. It turns out, anyone know what one of the big uses of big trees was back in the 1500s? Warships. Not just ships, but warships. This was national security, particularly for Britain. It turns out that it took about 2,100 tons of high-quality oak to build what was the ship that Victory, Nelson's flagship at Trafalgar. 2,100 tons of high-quality oak. Took a whole forest to produce that, and you had to have big trees. You couldn't have trees that were only 20 years old. You needed 300-year-old trees for some of these things, and you can go down to the USS Constitution and see it. Well, it turns out that one of the problems was people started to make iron in the 1500s, and to make iron they needed charcoal to reduce the iron from the iron ore to metallic iron. And so it turns out the two uses of oak were in conflict. In 1558, a law was passed forbidding, quote, the felling of trees to make coals for the burning of iron, unquote. But the weld of Kent and Sussex, which is where they made the iron, was exempted. So good government planning, you put in a regulation, then you exempt the people who are relevant. Okay? Perhaps because of lobbying by the thriving iron industry in that area. And still the price of wood continued to climb. In 1559, a writer complained that the price had risen from a penny to 2 shillings. I don't even know what the conversion between pennies and shillings is, but I think it's whatever it is. That's like at least a factor of 4, right? If not a factor of 10, something like that. By 2 shillings a load by reason of the iron mills. By 1581, the shortage of wood for shipbuilding was so serious that a further act was passed forbidding the felling of trees within 22 miles of the Thames, within 4 miles of the great forests of the Weald, and within 3 miles of the coastline anywhere. Because you got to get those big trees down to the water, right? So you had to be close to a river or the coastline. If it was a really landlocked tree, you could cut it down, I guess. But the consumption of wood by the glassmakers continued, and so it wiped out the iron industry, basically. And what happened? Saugus Iron Works come up here to Saugus, go take a field trip, okay? They started coming over here to cut down the trees over here for their iron making, because they couldn't do it in England. Saugus Iron Works was like 1608 or something like that. It was pretty early on. By 1615, England was facing an energy crisis. A royal proclamation in that year lamented the disappearance of the kind of wood which is not only great and large in height and bulk, but hath also that toughness and heart, as is not subject to rive or cleave, and thereby of excellent use for shipping. And so at last that country was forced to turn to a source of fuel which had been known for centuries, but which few had chosen to use: coal. And what happened when they started coal? They got into coal mining, and when they got into coal mining, they had water in the mines. And what did you need to get the water out of the mines? You needed a steam engine to pump the water out of the mines. And the mine operators needed to understand how, whether they were burning more coal to get the water out of the mine than the coal that's coming out of the mine, right? So you needed to know the efficiency of your steam engines. So you had James Watt coming along with steam engines, and then you had to figure out the efficiency, and that was the beginning of the science of thermodynamics. So you can kind of tie this little stream all the way from shipbuilding of the great man of wars in the 1500s all the way to the reason we developed thermodynamics, to understand how to pump water out of the coal mines, because you couldn't use the charcoal. Isn't that a great tie-in? Anyway, whether it's true or not, who knows. This is a handout I just happened to see in a magazine this week, written by IBIS Associates. Professor Clark, his first student started IBIS Associates, which is a consulting firm that looks at material substitution primarily in the automotive industry. And here's an article of, they did an analysis of use of magnesium in automobiles. So you can look at that and see some of the types of things. It's basically a material selection problem, so far as that goes. I mentioned the productivity increase in steel, give you an idea of how that works. What do they do? Same old steel, there's nothing new about the steel. But Chaparral Steel is kind of an interesting company that was started as one of the mini mills. Chaparral had a practice in the 1980s of having their foreman from their shop go once a year on a sales trip with one of the salesmen to the customers. And Chaparral started out making rebar, reinforcing bar for concrete, which is kind of about the cheapest grade of steel you can imagine. And originally when the mini mill started, that was the only quality they could build, was kind of the lowest quality. Anyway, what they learned is rebar comes in a number of different sizes. The smallest is 3/8 of an inch diameter. It's called number 3. And 4/8 of an inch is called number 4. And 5/8 is number 5. Anyway, very clever numbering scheme, all the way up to 13, which is 1 3/8 inch diameter rebar. It turns out there was like a 15% premium in price for 3/8 inch rebar. Well, the reason for that, and these guys learned this, they said, oh, we can make more money. It's a company, profit-sharing company, and they post every week the profitability of the company on every bulletin board in the plant, so everybody knows how much extra money they made that week. And it really incentivizes these people. And so they said, gee, we want to get that 15% premium for selling the smaller rebar. Well, the reason there's a 15% premium is if you're rolling the small rebar, you don't get as many tons out the end of the mill as you do if you're pushing the bigger stuff out. Turns out the hot band typically is going out at about 60 miles an hour through that mill. And if you try to go faster, there's all kinds of instabilities that occur, and you all of a sudden have a hot band of 1,500 degree steel whipping around the plant, and if anybody gets caught by it, it'll just cut your arm right off like a hot knife through butter. The nice thing is it cauterizes at the same time because it's hot. Hey, I mean, when I worked in the steel company, there was still, even in the 70s, about once a year someone got impaled. Back in the 30s, we had a beautiful, my second daughter was born in a hospital in Bethlehem, Pennsylvania. Wonderful hospital, just down from the steel mill. Why? Because they take steel makers there, or steel workers there every week. And so the steel company had built them a big hospital since they were maiming them otherwise. Anyway, this is what happened at Chaparral. They went back and they tried to speed up the mill, and they had the same problem everyone else in the world did. But then they thought, well, rather than going faster, maybe we should try to go slower to make the 3/8 inch rebar. So what they did is, here's the hot band coming in, and then they split it in two. And they had two bands going through. And then a little bit further down the road, they took those two bands and they split it into 4. And so they got 4 times as much through. If you go half the speed, but 4 times the number of strands, you get twice the productivity. So that's one way. And it kind of shows thinking differently is a very profitable way of looking at things. And I've actually sort of tried to make a career out of thinking differently. I remember I learned in second grade when I was at an Easter egg hunt that you don't follow the crowd. What would happen, ever been to an Easter egg hunt, and one child says, "I found one," and what does everyone else do? They all go running over there, right? And I did the same thing, only I was one of the last ones to get there, and I realized I'm never going to find an Easter egg with all these other eyes looking in the same spot. So I went in the opposite direction where no one else was. And that's where I found the Easter eggs, where no one else was looking. It's like a second grade soccer match, right? They all run to the ball. Then someone gets the ball over there, they all run over there. You know, the people, and when you get later in life, you learn that you should space the team out, right? And you should look at different things. But anyway, another thing they did is instead of in continuous casting where you that's not a very good picture, let's do this. Use this one. This is continuous casting, and this, they used to just kind of make rectangular ingots as a continuous cast strand that solidified, and then they cut it off with oxygen cutting, which you'll learn about later in the course. And then they have to roll it to the shape of an I-beam. Well, what Chaparral did is they changed the shape of the mold from a rectangle to a dog bone, and ended up essentially casting something that only has to be rolled 7 times rather than 26 times through the mill to get it to the final shape. It turns out by doing that, they got a finer structure, and they could make 50 KSI steel identically to composition and rolling practice as 36 KSI steel. If you go look at American Institute of Steel Construction, they have 36, 50, and 70 KSI steel for building bridges and buildings. Used to be a premium to get 50 KSI steel. Chaparral ended up, when they developed this process, they just stocked one thing. You order 36, they ship it to you. They order 50, they ship it to you. It's the same thing. Had the same weldability because it had the same chemistry, but they had cooled it more quickly in solidification and ended up with significantly better properties because they had changed that, and they also rolled it more efficiently. Tremendous increases in productivity, and that's why the price of steel in real dollars is about 1/4 today of what it was 20, 25 years ago. Give you another story. The U.S. Army, about 10 years ago, decided they needed to look at what materials they would be using in the future to make tanks and things. Guess what they concluded after spending several millions of dollars on this study? They were going to use steel. They also had to study to figure out what material did they purchase the most of? Steel. Now, I could have told them that, and they could give me a couple million, right? Wouldn't have had to do the study. Now, there's another thing. It's not just strength that you're interested in, it's fracture toughness. This is the ratio analysis diagram. I'll tell you the history of that in a second. But what is fracture toughness? Well, actually, before I give you that, I'll give you this. Turns out, Bob Sprague again, using him from General Electric, he says, material scientists think that properties are controlled by microstructure. Metallurgists know that properties are controlled by defects. Defects in the materials actually reduce the strength and degrade the properties more than we would like. And I use this example all the time. Take a sheet of paper. Paper is actually a brittle material. I can load up the edge of a piece of paper, load up the edge of a piece of paper like this and pull with several pounds of force and it won't rip. If I put a defect in there, it takes ounces. That defect, that flaw, that initial crack significantly weakens the material. And we'll talk about fracture mechanics later, but for a structural material, you not only want strength, you want toughness as well. And this is the ratio analysis diagram developed by Dr. Polini after World War II. People didn't understand fracture toughness very well during World War II. Griffith was a scientist in England in 1925, and he came up with the fundamental equation of fracture mechanics, which we'll go through next week. But in any case, he basically said that the toughness of a material is related to the strength times the square root of the crack length, the flaw size. Okay, that's the fundamental equation. That was in 1925. What happened 15 years later, 20 years later, is they built about 5,000 Liberty ships and T2 tankers, and about 200 of them had major cracks, and a few of them sank, just broke completely in two. Actually, I should have brought that book. I have a copy of that. MIT library was throwing it out, and one of my students bought it for $1. But I have a copy of the 1946 report. In 1945, the U.S. Navy and the British government formed different groups to study what had happened to the Liberty ships in World War II. Why did some of them just break in two, and why did they have so many fractures? They had been designed to all the best civil engineering strength calculations and everything at the time. Well, it turns out it was brittle fracture. And it turns out 3 places for the next 10 years, from 1945 to 55, really helped define the science of toughness. One was the Naval Research Lab, and Dr. Polini, who when he retired actually came here to Ocean Engineering and was a visiting professor while I lived down on the Cape and taught courses here. And I don't know if you still use one of his books, but he basically developed some courses. He developed the ratio analysis diagram at the Naval Research Laboratory, which plots strength versus toughness of a material. Then another place was the British Welding Institute got started. And they've grown to be one of the world's premier welding research institutes, and they do a lot of their work for the offshore people now because that's where the money is. And the other place was right here at MIT in the materials department with Professor Cohen and Averback and a few others, funded mostly by the Office of Naval Research. But the ratio analysis diagram plots toughness versus strength, and on here, using the fundamental equation of fracture mechanics, you can plot the critical flaw size. And that's what all this stuff is: ratio of fracture toughness to yield strength, 1 to 1. Well, if it's 1 to 1, then your critical section thickness in inches, or your critical flaw size, is about 2.5 inches. Well, you can, if any of you know anything about submarines, you can, without getting into classified information that you will have to shoot me if I tell you, you realize that we're on that order, okay? It's not an inch, it's not 4 inches, somewhere in between, right? I know the real number, so do some of you, for typical hull, although, anyway. So you want to, what type of strength? Well, you don't want to go, according to Polini, above 180 KSI. The Navy one time had a program for HY 180 steel. Actually, we're down in the 130 range right now. Actually, we're in the HY 100 is what we're building hulls out of right now. But in fact, the Seawolf was an HY 130 submarine when you got to the weld metal, because they had a high side chemistry. I don't know if you want to talk about the Seawolf sometime, but I was one of the 5 people brought in by the chief engineer of the Navy to oversee what General Dynamics was doing, to make sure that they were doing it right after the failure. If you go to different strengths, you could have critical flaw sizes here, critical section thicknesses at higher strengths of 1 inch, 0.6 of an inch, 0.2 of an inch. If you get to really high strength steels, 1/10 of an inch is a critical flaw size. Now you have to understand, if this was a ceramic, we'd be talking about critical flaw sizes that are less than a human hair, not 1/10 of an inch, because the fracture toughness of a ceramic is significantly less. So this is a ratio analysis diagram, and you can go back and you can do the fracture mechanics and figure out all kinds of wonderful things. If you do the same type of diagrams for titanium or aluminum, you can look at what you might want to build a deep diving submersible out of. But it turns out the fracture toughness here for aluminum is about 5 times less than the typical values that were on the steel plot. Has 1/5 the toughness of steel. It has about 1/3 the strength. Has a similar type of curve. Titanium has about twice the toughness of aluminum and has about double the strength of aluminum, but it's still significantly less than steel. I once plotted all 3 of these on one plot, which I'll show you, if I can dig it out here. And I plotted it with a few other materials. And when I used to go around and talk about why steel was an important material, I used this plot all the time and irritated all the ceramists and polymer people in the room. But it's the truth. This is fracture toughness versus yield strength. Here's steel. Steels tend to follow this band. Titanium alloys are down here, aluminum alloys down here, and composites are down here. Steel has, you want to be out as far out here as possible. Over here you have plastic general yielding. It means you can hit this thing with you know, a mortar round, a shell, and it's going to deform and bend and absorb a lot of energy. Good armor, high toughness, not necessarily the highest strength, but tremendous toughness, so it will deform before it breaks. Over here, you're getting to brittle materials. Not much toughness, a lot of strength, and therefore they're going to crack on you. This fracture toughness divided by yield strength, when it's less than 0.6 inches to the 1/2, that's supposed to be squared. Sorry, it's supposed to be a square on each one of those. I'm sorry, no, it's not squared. Actually, take it back. No, that's correct. Kc over sigma y is 0.6 inches to the 1/2. So that's correct. The plot's correct. Sometimes we plot this as this whole quantity squared, and so that would be in inches rather than square root of inches. But anyway, if it's greater than 2.5, then you got great plastic yielding. Most of the structures we build in the world are here in what we call elastic plastic range, and we use elastic plastic fracture mechanics for it. Turns out you can use steel at very high stresses. You can use titanium at lower stresses. You can use aluminum at lower stresses. You can use polymers in here. They actually cross this region. But you're getting very, very low stresses. Composites, many of the composites end up being somewhat brittle. They're outside this middle band that you'd like to design things in. Ceramics that never even saw the light of day. Ceramics are brittle. And people used to talk about the future of structural ceramics in the 1985. I remember I lived in Tokyo for a year, and they had a ceramics conference at Shibuya, not Shibuya, Shinjuku, if anyone knows Tokyo. 2 million people attended. I mean, they called it ceramics fever. People that didn't know anything about materials, they'd go just to see the fancy ceramics. And they have these little ceramic scissors and stuff. Anybody ever use ceramic scissors? I don't have to bring the ceramic scissors in. I have a couple in my office. The problem is they're all chipped. Okay, they can hold their edge forever as long as they don't break. Okay, but they're sharp forever as long as they don't break. Okay, you look at them cross-eyed and they break. But aside from that, so steel has that exceptional combination of strength and toughness. There are some things like cobalt alloys that can be made even tougher at the same strength as steel. They cost about 50 times as much, but they're, you know. To give you an idea, one of the things that came out of the Naval Research Lab in Polini's work was the explosion bulge test. Anybody ever heard of the explosion bulge? Nobody's ever heard of explosion bulge here? Typical. Every Navy SEAL has to pass it. Okay? It's about as archaic a test as you can imagine. They basically take a plate and they weld it, 2 plates together, make this big square plate. Might be 1 inch thick, 2 inches thick, whatever the thickness is they're interested in. And they put it on a die, and the whole plate's like about 4 feet square. So this is not a cheap test. And they take it out to some weapon center somewhere, I can't remember which one. And they basically let a charge off about 4 feet above it. And it presses and forms a dome into the die. And then they give it another shot and see if it fractures. And they see how much of a bulge they can put in this thing before it just shatters. Sometimes the first shot shatters it just like glass. They decide that's not a good steel. That's not a good welding process. And this is actually what they've got here is different testing temperatures, the results of an explosion bulge at 140 degrees Fahrenheit. You go down in temperature and steels become more brittle, and some of them just shatter like that. Okay, but you did that with aluminum, you look at it cross-eyed, it would shatter. So there is an advantage to some of the steels, but the Navy still qualifies things. A year ago, I was asked to serve on the HSLA 65 review. Anybody know what HSLA 65 is? I thought you guys were shipbuilders. The Navy decided they could not afford to redesign the hull of the aircraft carriers. I don't know how many billion, it probably cost $1 billion to redesign. So for the next 40 to 50 years, they're going to use the same old Nimitz class hull. The problem is, aircraft carriers gain weight at a rate of 250 tons a year. Okay, if you go back to 1960 or whenever the Nimitz was designed, and you plot the weight of the carriers, and these are even the carriers that are already out there. You just put new stuff on them, and they gain weight. I think the number is 250 tons a year. Well, you go 40 years times 250 tons, you're actually talking about a reasonable amount of weight gain. Plus, it's usually up in the superstructure, right? And so it's not down the keel, so they become less stable. So just kind of looking at this trend line, they decided they had to get some weight. They wanted to get 2,000 tons out of the superstructure, and they had to go to higher strength steel. So they wanted to qualify HSLA 65. And so they brought in a half a dozen of us and had us review what NAVSEA had been doing to qualify this, because they didn't want the same thing to happen that happened with the Seawolf. The Seawolf, every time the Navy has ever changed the steel, when they went from the old 52 KSI or whatever it was, EH52, or DH52, whatever the ABS rating steel was they were building submarines out of in World War II. It was kind of a yield strength of like 40 KSI and a tensile strength of greater than 52. I think the Nautilus was one of the first. Was the Nautilus the first one in the 50s, built out of HY80? Anyway, they developed this HY80, and when they went to the first HY80 subs, they actually had to weld them with stainless steel electrodes and degrade the strength back down to about 40 KSI because the welds were under strength. And the reason was they were getting hydrogen cracking. So they had to do big studies in the 50s and 60s about hydrogen cracking. It took them 5 years to learn how to weld a submarine without getting cracks in it with hydrogen cracking. Well, we stayed with HY80 until about the mid-1980s, and then they put some sections of HY100, which is basically the same alloy, but just tempered to a higher strength level than HY80. They built a couple of sections that went into some existing subs. They didn't make the whole hull, they just did, a section out of the middle or two. In fact, my first student ever here at MIT was in charge of that electric boat, that project. And those ships were out. And then they decided that the Seawolf, the first of the 21st century submarines, attack submarines, they sold that program to Congress. You have to remember that what happened was in 1980, the Soviets came out with the titanium sub, the Alpha. And if you want to see the type of welding done on the Alpha, here's a piece of titanium electroslag weld. I'll pass that around. That's 2 inch, or is that 1.5 inches, 2 inch, whatever, thick titanium, and the weld zone is that great big area. It's about 1/2 the whole thing. That was made at the Oregon Graduate Center. The first electroslag titanium weld made in this country, to my knowledge, was made over in my lab, about 1981. The Soviets were already using it to weld the Alpha. Now, I didn't tell you that. I didn't say that on tape, but it's 20 years, more than 20 years since I learned that. So, and I won't tell you how I learned it. But in any case, the Soviets had built a full-size submarine, the Alpha, in the early 80s, and that created a big flap. They had leapfrogged us and all this other stuff, and the Navy was starting to build another submarine. They're going to build it out of steel. And I've been to 2- and 3-day workshops where the people in the Navy were going to build all composite submarines to leapfrog the Soviets, except no one knows how to do it. I remember I went to one of these workshops and they brought in, I think it was the USS Patrick Henry. They put up a picture of the ship, and this had been decommissioned, but they had all the cutouts that had been put into the submarine over the 20-year life or whatever the sub had gone through, and it just looked like a patchwork quilt, right, where they had to cut the holes in the ship. And they told the composites people that when you design a submarine, you have to be able to cut it open. And we go off for our 1 day. I went off with the titanium folks because I'd been welding titanium. And we came back on the 3rd day, and the polymer guys, the composites guys, come in and they say, well, we're just going to put doors wherever we need to take something out of the submarine. And of course, any of us who ever walked through a submarine yard and seen what's inside a submarine, we just laughed, okay? First of all, if you knew what part was going to break, you would fix it before you put it in there. And there's not these great big corridors down the middle of the submarine so that you just kind of take this big piece of equipment and pull it out into the corridor and run it down the corridor to the door, okay? If you've ever been inside a submarine, you know there's not a lot of extra room in there, okay? And so you have to cut the thing wherever the problem is. But they didn't understand that. They're just, aside from the fact that you couldn't afford to build a composite submarine. By the way, I already put it away, but the X-33 space plane, that thing that sized that house, I can't remember, I think it weighed 4,000, yeah, it was about 4,000 pounds, cost $50 million. That's $12,000 a pound fabricated for the composite, okay? I'm not kidding. It's not the largest composite structure ever built. The B-1 bomber is, and what do they cost? $2 billion a piece or something? Not B-1, but the B-2. You know, the stealth B-2. It's about $2 billion. It's probably bigger as a composite, but you know, you're talking about fancy high-strength composites will probably cost you somewhere on the order of $1,000 to $10,000 a pound fabricated. So if you run those numbers, did we need to hold this workshop? No, we didn't. But someone there in the management thought, well, we'll build composites. Anyway, so they sold Congress that, well, they had to tell Congress, we're going to build a steel submarine. Well, Congress didn't like that. The Soviets already had a titanium one. Why do we want to pay for a steel one if the Soviets have a titanium one? Why can't you go to composites, right? Well, you want to see the price tag on a composite submarine, and then you can't repair it if something goes wrong. And in fact, that's what happened to the space plane. There was no repair procedure. There's another tank sitting out there in Palmdale, California. I've seen it. And they don't know what to do with it. They don't know how to repair it. It's one of the reasons they killed the program. So they built 2 of these $50 million objects before they broke one and then decided the other one was junk. Anyway, so there's some sort of serious problems of just kind of going to these advanced materials. So the only way they could sell Congress on a steel submarine is if they went to higher strength. So they agreed the Seawolf, the first one would be HY100, and the next one, or the next, somewhere down the line, and of course they changed all this when peace broke out in the early 90s, would be HY130. Well, the problem with the Seawolf was when they welded it, they had the chemistry on the welding electrode was on the high side. You know, there's a range for manganese, there's a range for carbon, there's a range for silicon, there's a range for nickel. Turns out it was a very rich electrode. Everything was on the high side of the range. Everything was within spec, but it was on the high side of the range. And they welded with this, and it turns out the strength of that weld metal was more like HY130 rather than HY100. And they got a different type of cracking they'd never seen before. They welded up 18% of that hull, and a grinder was grinding the hull smooth. You can't even have the weld reinforcement on the outside of a submarine. Too much turbulence in the water. Makes it noisy, right? And he was grinding the weld smooth, and he noticed they had done their ultrasonic testing and everything, and they had not found any flaws, but they weren't looking for less than 1/8 of an inch flaws. And this thing was full of a little less than 1/8 of an inch flaws. And this grinder saw that some of the grinding swarf was kind of sticking on the steel. Steel's can get a little residual magnetism, right? And they were basically doing a magnetic particle inspection with the grinding swarf. And he said he thought he ought to tell somebody that he saw these little lines where the grinding swarf was sticking on the weld. And they went in, and of course, then they knew not to look for 3-inch cracks, but to look for less than 1/8 inch cracks. They found it was full of 16th inch cracks. Had to cut out everything and start all over again. Probably cost $500 million when it was all done. Was not a happy day. Anyway, every time you go to another steel, you have a problem. So they decided on HSLE 65, they wanted to get a second opinion on what the problems were. So they got a bunch of us together, and we told them what some of the problems were, and then they decided that we were too pessimistic. So they canned our committee. So I don't know what they're going to do about HSLE 65. It will actually work, and it won't have as big of problems, but there are some things that need to be done. So anyway, I have a quote from Rudyard Kipling: "Gold is for the mistress, silver for the maid, copper for the craftsman cunning at his trade. Good, said the baron, sitting in his hall, but iron, cold iron, is master of them all." See, so even Rudyard Kipling knew that steel was important. It's not just me. It does have a unique set of properties. Any questions on all of that? Let's talk a little bit about other materials than steel. Probably worth doing something, right? We've got another day on material selection after this. So let's take aluminum. Aluminum is higher cost by about a factor of 5 or 6 than steel. It's lighter, it's only got 40% of the density. I already pointed out lightweight's an advantage, particularly if something moves, like an aircraft. So aluminum is a wonderful material for aircraft. It's good for aluminum foil too. What's the largest application, largest single application for aluminum? Beer cans. There you go. Soda cans. 40% of all the aluminum made in the world goes into beverage containers. okay? And that's not for anything other than for that particular application. It has very good formability and corrosion resistance. So anyway, one guy who used to be director of research at U.S. Steel called aluminum the near metal, okay? It was nearly a metal. It was almost ductile. Aluminum actually is it's kind of an interesting metal. It turns out until about 1888, aluminum was more valuable than gold. In fact, I should have brought this book too. The royal cutlery, not cutlery, but the dinnerware in France, the King of France used aluminum dishes and forks and spoons and knives because it was more valuable than gold. The top of the Washington Monument, the little thing right on the top, it's like an 8-inch pyramid at the top of the Washington, it's made out of aluminum. Because when the Washington Monument was put up in, what, 1884 or something, aluminum was more valuable than gold. Why was it more valuable than gold? Because aluminum oxide is so stable, and it takes so much energy to refine it, people could only in the laboratory produce little nuggets of this aluminum from the aluminum ore. You had to go to sodium metal, which was produced electrolytically, and refine some of the aluminum with sodium metal to make aluminum metal. Charles Martin Hall in the United States came along around 1886, and another guy in France, Perot, independently came up with a way, if you took aluminum oxide and dissolved it in a molten fluoride at 1,000 degrees centigrade and ran a big current through it, you could get aluminum out the bottom. That's still the way we produce all the aluminum in the world. It's called the Hall-Héroult process. Charles Martin Hall went on to form a little company called Alcoa, Aluminum Company of America. Perot started Péchiney, which is still Péchiney Metals in France. But in any case, aluminum came along, and it has tremendous advantages when things when you need lightweight. It's lower melting. It has a problem in that it melts at only 1,200 degrees Fahrenheit, about 660 F, or 60 centigrade. And that means that its service temperature is typically limited to the 200 to 300 degrees F range. You can't go any hotter than that, or the aluminum starts to deform. I mentioned the brake calipers. People have tried to make brake calipers for automobiles out of aluminum, but the brakes fade when the brakes overheat because the aluminum starts to deform, and you're losing the pressure on the brake. The Concorde, now famous because of the tires, but the Concorde does not fly on speed, it flies on skin temperature. They actually have sensors, thermocouples on the skin, and it's an aluminum alloy, and if it heats up too hot, it will lose its strength. And there's enough frictional heating, they actually, when they're going across the ocean, I've flown the Concorde once. I paid the premium price coming back from Europe once just to say I flew the Concorde. Let me tell you, it's one of the smallest cabins, filthiest cabins. It's British Air, if anyone wants to know. And one of the worst meal services I've ever had, okay? But it's called super first class. And one of the disadvantages, everybody thinks they're first class, so everybody wants to board first. But it goes fast, and they're right in front of you. They have this big LED display that tells you what your Mach number is, and we got up to Mach 2.4 or whatever. And we left London at 5 p.m. in the evening on a Friday, and we got to New York City at 4:45 that evening. Okay, 15 minutes earlier, right? With time zone change. And the really interesting thing is you do not get jet lag. Everybody told me you don't get jet lag when you fly the Concorde, and you do not. And the next day, Saturday, it was raining in Boston. I got into Kennedy and had to wait 3 hours for my connection. My connection was 3 hours late because of thunderstorms in Boston. I got home about 11:30 at night. I'd gotten up in Vienna that morning and then had to fly to London to get the Concorde. And I was like 7 hours different. And I'd been in Europe for a whole week. So I was, on European time, 7 hours different. Didn't go to bed until 11:30 that night in Boston. Got up the regular time about 6:30 Saturday morning. Went off, did grocery shopping, mowed the lawn. I was out working in the yard about 4 o'clock in the afternoon, which is when usually jet lag hits me. And all of a sudden I realized I felt fine. No effect of jet lag whatsoever. So you don't get jet lag. The only thing I can figure is you're not getting dehydrated and everything, like in all the noise in the other planes for 10 hours. In any case, aluminum has temperature limitations. It has lower toughness than steel. It also has certain problems in it. It's much more stable as an oxide than it is as a metal, and that's a Achilles heel of all metals, is they want to go back to their native state, which is as an oxide or a sulfide. And so aluminum tends to have some stress corrosion cracking problems or other corrosion problems. This happens to be the washer from a Black Hawk helicopter. The Navy has Seahawks. The president flies around in a presidential helicopter, which is the same class. And this is the washer and the nut that hold the tail rotor on. This actually is gray because this is when they took these things out of inventory. This would have gone into a Seahawk. This came from a Black Hawk. But in any case, the Navy were the first ones to notice they were taking these things out of service because they had cracks in them. And then they found some that were sitting on the shelf, never been used, had cracks in them. And then one of them actually, this nut was on one that actually crashed in Arkansas and killed some people. It turns out that they had decided that the problem was the temper on this aluminum alloy. It's a high-strength aluminum alloy, and this little thing costs about $300, by the way. But if I told you everything that went into manufacturing it, you wouldn't want to make one for $300. It's actually some interesting technology that goes into this. But basically, stress corrosion cracking. We measured the residual stresses on this. Has 8 KSI residual stresses from the heat treating process. And it only takes about 5 KSI stresses to cause stress corrosion cracking just in the humidity in the air if you have the wrong temper. So they were in the process of re-outfitting the entire fleet when this one went down. Now remember also, this is the same thing that was on the president's helicopter. Okay? So those things happen. But that's one of the problems with aluminum. Magnesium, let me do that quickly and then we'll finish up for today. Magnesium has about twice the cost of aluminum. Now some people would argue that it shouldn't necessarily have twice the cost of aluminum, except there was sort of a cartel that was formed after World War II. And Dow Chemical decided they would take the aluminum business, and Alcoa agreed they would not compete in the magnesium business. So Dow had the magnesium business, and Alcoa would not compete with them, and they would just take the aluminum business. They would both deny that. They would probably say this is libel, slander for me to say this on tape, but it'll go on the web. There's plenty of evidence for it. Okay. There's actually no scientific reason why there should be a factor of 2 difference in price between magnesium and aluminum. However, if you track it for 40 years, it's been a factor of 2 in price. Now, but magnesium is about 1/4 the density of steel. It's very light. It's reasonably strong. Its problem is it's even more reactive. It's more susceptible to stress corrosion cracking. If you were to hit it with a hammer and come back a few days later, it will probably have a crack in it where you dented it with a hammer, just from the moisture in the air. You can't weld it because of the residual stresses. You can't fusion weld it anyway. You can adhesively bond it. When they put it in automobiles, they typically put it in the dashboard because there's no particular corrosive salts. Yeah, when they put it on magnesium wheels on the cars, most of them are aluminum wheels, but in the old days they used to spend money and have mag wheels. They had to give it a chromate conversion coating and paint it and do all this other stuff to keep it from corroding, and then it looked good for about 2 years, and then it looked like it was just a white rust all over it. So magnesium is very light, very difficult to fabricate, very susceptible to stress corrosion cracking. It's such a good corrodant that the Navy actually built a super corroding alloy, which was just a composite of magnesium and carbon. And you could take this down in a plastic bag and under the ocean, and you could either break it open down there, and it would corrode fast enough to generate heat to keep the diver warm in cold water. Okay? Or alternatively, You could use it for salvage operations. You basically could crack it open under the ocean, and it would form its own hydrogen bubble, okay, from corroding, because the reaction gives off hydrogen. And you now had a gas to lift the salvage stuff up to the top. You didn't have to pump gas down to the ocean, right? You just let it corrode right there. One of my colleagues was doing some studies on some of these alloys, and he was trying to polish them in the laboratory. It was corroding in the polishing compound faster than he could polish it. Okay, it corrodes just great. In fact, typically used as anodes. All of you own some magnesium at home in your hot water tank. There's a magnesium anode that keeps your steel tank from rusting away. The magnesium's being consumed. Most of the pipelines in the country, they buried magnesium in the ground, electrically connected them to the steel. It's called cathodic protection. One of the bigger applications of magnesium. As a structural material, well, if it'll never get wet, if it's something to stay indoors, it makes good ashtrays or things like that. But if it's going to be exposed to the environment, if it has to be fabricated into some complex shape and joined, then magnesium has its problems. So that's enough for today. I'll see you next week. Thanks.